is Ismaeel Zaman. I'm a PhD student here at the University of Bristol, and my research is on the aeroacoustics of propeller boundary layer ingestion. So, in this presentation, I'll first begin by giving you a background of what boundary layer ingestion actually is, followed by our experimental setups that were designed to investigate it, followed by some of our results, and finishing up with some final remarks. So what is boundary layer ingestion? So for those of you who may not be so familiar, it's where you take your propulsion system, whether that be a propeller or a turbojet, and place it near your fuselage such that it is ingesting the airframe boundary layer. So if you see the aerodynamic picture at the bottom illustrates this quite nicely, where you have your airframe boundary layer that is being ingested by the propulsion system. So in doing so, you can potentially re-energize the wake, reduce drag, and therefore potentially significantly increase your fuel efficiency. But because your inflow to your propulsion system is no longer uniform and potentially more turbulent, this does raise the concern of increased environmental noise. So to investigate this, I designed two experimental setups. The first one is the zero pressure gradient boundary layer, so flow across a flat plate. And then the second is a adverse pressure gradient boundary layer, where you would where the flow would develop over a curve to simulate a sort of a buried configuration. So for the flat plates, we vary the incoming boundary layer properties, also increasing the tip gap between the propeller and the plate, and varying the propeller thrust. In the S plates, we also have the addition of varying the propeller location along the curve. So common to both of those configurations is the propeller rig. So this wasn't a simple thing to design. It have special specifications and requirements. First thing being that the nacelle casing had to be somewhat aerodynamic to reduce its effect on the flow field. We have a 3.2 kilowatt motor inside, and with that amount of power, we can generate quite a lot of heat, which necessitates the use of a cooling system, which, similar to Liam's, uses a compressed air system, but we also pass it through a vortex tube to lower the temperature even further. Inside here, we both have a load cell and an angular encoder. So the load cell, as Nora and Liam's previously demonstrated, can give you your thrust and torque of the propeller, and your angular encoder can give you your absolute blade position through time. So in terms of instrumentation, we have our split into far field and near field. Far field, we have our two far field microphone arcs filled with brass microphones. And in the near field, we have our heavily instrumented plate. So here is showing for the flat plate configuration, where we have both static pressure taps and surface pressure transducers. This can help categorize the development of the boundary layer as well as the effect of the propeller on that boundary layer. So here's a short clip of the setup. So we see both arcs, and currently this is set up for our hot wire measurements to properly characterize our flow field. So we can input a set of coordinates, and we have an automated traverse system to go through and measure all those points, synchronized with the angular encoder. You'll see the results of that later on. So first beginning with our flat plate, see both arcs, and then we'll take you through some of the results now. So the first thing we have to do is characterize our boundary layer that we see. What is the propeller actually ingesting? So we have three tripping devices that we placed upstream to generate our three boundary layers. Trip A, B, and C. C being the thickest at around 10 centimeters, which translates to about 2/3 of our blade radius. And what you see here, if you see our RMS figure for our boundary layer profiles, we see that trip C demonstrates quite a large increase over the others, and we expect this to see an increase in noise. And indeed we do. So this is the directivity patterns from both arrays showing OASPL. And what we can clearly see is that, so if you look at the black line, that is the isolated propeller case without the plating, without ingestion, and the lines as you go progressively louder would be our increased ingestion, increasing boundary layer thickness. And we can see for the overhead array, this translates to a large increase in noise, particularly downstream. Whereas in the side array, this increase is not really seen, but we do see something in the upstream. So we have two hotspots here. We have one in the downstream portion of upstream in the overhead array, and the upstream portion in the side array. So let's look at the spectra in these two locations. So for the overhead array, we can clearly see that the increase in noise is very obviously due to a large increase in broadband noise from turbulence ingestion. But in contrast, we see that in the side array, the broadband increase is not so clear, but the internal increases are still quite significant. So that was for one particular operating condition. If we go to different operating conditions, go to higher thrusts, what happens then? So we see here, so from left to right, we're going to higher thrust. So at lower thrust, you can clearly see that the separation is still present, but as we go to higher and higher thrust, the effect of the boundary layer on the emitted noise reduces. So as we increase our thrust, sensitivity to our turbulence in the boundary layer does reduce. So let's have a look into the sort of mechanisms that might generate this. So we phase averaged our OSPL, our far field microphones with the encoder signal. And so in BLI, we have generally 4 phases of the propeller. One is the approach, where it's approaching the plate when it's perpendicular, and then when it's going away from the plate, and then other angles when it's not ingesting the boundary layer. So if you see the plots on the right, you can imagine if on the left, from left to right, we go from non-ingestion to the approach, to the perpendicular, to the retreat. What we can clearly see is that the peak noise generation happens at about -10 degrees. So during this approach phase, just before the perpendicular phase, and we have an increase between the thicknesses of about 14 decibels. So to look into this further, into the flow field, we can see we measure the hot wire line just in front of the propeller from the surface to the hub. And so this is our mean velocity. So we can see that if during the non-ingestion phase, the blade is coming towards the plate, and then just before it becomes perpendicular, we have a sudden sharp suction and then acceleration. And it's at this point where we have the high RMS, and this is when noise is being generated. So let's just zoom out a bit and see what the flow field as a whole looks like. We can clearly see upstream of the blade. As the blade passes, we have a pulsation upstream, and then quite interestingly, we can actually visualize the tip vortex that is being generated and convected downstream before crashing into the plate. If you want to have a better look at this, we also have some phase PIV results, where we can see this a lot more clearly. So that was it for the fat plate results. Let's see how the adverse pressure gradient compares. So here's the experimental setup. This is our curve, and in this case, we have instrumentation along the center line. So the first thing we need to establish is, do we indeed get an adverse pressure gradient? So to begin with, we plotted the results of our surface pressure taps. And we can begin to see that in the beginning, we have a favorable pressure gradient for a sharp change, and it goes very, very strongly adverse before coming to a peak at about 80 centimeters downstream, and also a peak in the RMS, and then a slow recovery. So these 3 key positions were taken to record our acoustic measurements. And so from the detailed hot wire survey that we saw in the video earlier, you can see that this is now what the flow looks like. So at that point where the adverse pressure gradient suddenly starts to begin, we can see that this is where we do have a degree of separation. And we can also see that there's a very strong interaction between the propeller blade and the turbulence in the flow. And if you look at the plot in the bottom right, you can see how the turbulence measured here for the black line is our A2 configuration, and the 3 boundary layer lines from the flat plate configuration, there's quite a massive difference. And this translates to a massive increase in noise over the flat plate configuration. So the green line is the thickest trip case for our flat plate, and the black line is our current case for the same operating condition. And you can see that there's a massive increase in noise, about 6 decibels downstream, and in the side array we see the same 6 decibels, but across the full polar array. And if we take a closer look at the spectra, we can see that this is due to a massive increase in harmonic tones associated with higher ingestion. And also, quite nicely, we see a massive amount of haystacking. So for those of you who may not know what haystacking is, it's the highlighted humps around the blade pass frequency. This occurs when your broadband noise, which is typically normally a more straight profile across the frequency range, becomes so correlated with your blade's passing frequency that it starts to form humps around those tones. So that's for the overhead array. For the side array, we do have an increase in broadband over the flat plate case, but not as significant in terms of envelopes. So this is my last slide of results. We can see the effect of changing our streamwise location. So for the what is most obvious here is that you see the purple line here is our most upstream case, and this is where we see a massive reduction in broadband noise, which is, as you can imagine, from the massively reduced level of interference ingestion from the boundary layer. But the last two positions are generally quite similar, with the 80 centimeter being slightly louder. So some conclusions. Boundary layer noise generation is quite sensitive to boundary layer properties, but this does reduce as you increase your thrust. An adverse pressure gradient does significantly increase your level of ingestion and associatedly massive increase in noise. So there was a massive test matrix. I've only presented some key results here today, but it has large portions of that data set have been sorted and documented and been made available on Zenodo, accompanied by cleaned and watertight CAD geometry for use for CFD simulations, which has already been carried out by other partners in this project. So hope you found it somewhat interesting. Thank you very much. And take any questions.